get into it. And so I also want to clear up this slide right here. I was watching this, reviewing this at the end, and of course I did another like slightly dyslexic thing where I wrote these things backwards. So recall here where we left this, we came up with 4 equations and 6 unknowns, right? All of these normalization constants that we have to find simultaneously for the various regions, the 3 regions of the tunneling problem, okay? And so last time, so I got this transmission thing backwards. And so the idea is the 5th equation that we can come up with, right? So here's 1, 2, 3, 4, and then 5, right? Is noting that the transmission probability of this particle is going to be a ratio of its amplitude in region 3 to its amplitude in region 1. So I had those backwards. So we'll say it's, wave function of right moving particles in region 3 over the wave function of right moving particles in region 1. And of course, we recognize here that the reflected wave in both region 1 and 2, those are important for knowing how the particle is going to, undergo that forward motion all the way through, okay? And so what ends up happening is this idea now reduces to be the square modulus of a prime, right, the region 3 normalization constant, over the square modulus of the region 1 constant, okay? And so what we can do from here, so the reason why this gives us a 5th equation is because if we do some algebra on this situation, oops, let me open up my cheater notes here, okay? If we do some algebra, so I'm going to say ... algebra, we can actually come up with an equation for this transmission probability. And that looks like the following. So I'm not going to require you to do this algebra, but this comes from, I'll rewrite that again, a prime squared. Let's make that look a little bit clearer. So the a prime squared over a squared, okay? And all of that, when we do the algebra, plug in those equations, okay, really, by using the wave functions, right? Then we get this equation. Okay, so here we notice that we no longer need K, we only need kappa, okay? So I'll remind you that kappa was equal to 2m v minus e over h bar squared, all square root. And now this eta that we see right here, okay, that's the ratio of E over V, okay? So that is a ratio of the particle's kinetic energy to its potential energy, all right? And so now what we see here, there's a couple things that are going on in this figure, okay? So this left figure here, you can see incident energy in terms of E divided by V. Okay, so this figure is when E is less than V, right? Because you can see, for example, at this number 1 right here, that's when E is equal to V, right? And then similarly right here on this graph. But now you notice, for the rest of the scale on this right graph, this is where E is greater than V, okay? And so, of course, the transmission probability is going to be a number 0 to 1. 0 meaning 0% chance that it transmits through. So when t is equal to 0, no tunneling is possible. So in other words, it doesn't make it out of the other side, okay? And of course, when t is equal to 1, this is like the perfect case where the particle just moves through there unscathed, right? Which, as you can see from the graphs, is also not possible. It can't quite hit up to that 1 value. And I'll show you, I'll describe these 2 figures in a moment, okay? And so what do we have going on? So now there's also these numbers, okay? And those numbers have the value of L, let's see here, times root 2mv over h bar squared, okay? And so what these numbers are indicating, they're showing us what happens as the length of the box is increased, okay? So for example, you can see on the scale here, 2, 4, and 10, right? So as you can see, as the length of that box decreases, if I pick a point like, let's say, right here for the same constant incident energy, right? Let's suppose the incident energy is 80% of the potential, okay? So if, let's say, the potential energy was 10 electron volts, the incident or kinetic energy would be 8 electron volts, right? So now you can see if that's the case, and if this length of the box is fairly narrow, there's a really high probability that it'll make it through, like 35% chance, okay? So now, and that 35% chance is what really gives us the scaling down of the amplitude, okay? And so really that is to say 35 out of 100 particles will make it through, all right? And so now if I scale down here so you can see when the length of the box is doubled to that value of 4, the transmission probability goes way down. And if the length of that box goes all the way up by, to a factor of 10, so 5 times greater than it was for that number 2, you can see it doesn't transmit at all, right? And so for that case, when the length, is that factor of 10, so that's a relative scale, right? But you can see we have to really crank up the energy for it to transmit, okay? So now something also cool happens when we look at the situation when E is greater than V, okay? So you can see this curve right here to the same number 10 curve, so it's really starting to take off, and now it really jumps up. And what's pretty cool about this, what I think is cool about this, okay, in the case when they're 1 to 1, right, it just shoots way up to damn near 100% intensity, or 100% transmission probability, very close to it. It's not, it doesn't quite hit that value. But then what's also neat is as you increase that incident energy, you get this oscillatory probability, which is just a function of this being a wave property, okay? So when the length of the box is quite narrow, this number 2 right here, so that's where this curve takes off. And interestingly, it doesn't take on that oscillatory nature. It's taking on some exponential growth, okay? And so that just gets into some of these peculiarities of changing the length of the box or changing the energy of the particles as they're fired at the, or not really the box, but the barrier, okay? So now